YouTube. In this video, we're going to formally define what we mean by a compound probability and use the formulas that are associated with them. Okay, so let's go ahead and get started by what we mean by a simple probability very quickly. When we talk about the probability of an event, we could call this the probability of, say, some event A. What we're really doing is we're finding the number of outcomes in A, the number of ways that A itself can happen. So we say the number of outcomes in A divided by the total number of outcomes. So we say total outcomes. And we say visually with a Venn diagram here, we could look at it this way. We could say, well, this is the total number of ways something can happen. We're concerned with only those that can happen in event A here. So when we say the probability of event A, we're saying, well, how many things are in A to begin with divided by the total number of things here, okay? So if this is what we mean by a simple probability, here's what we mean by a compound probability. We mean things like this. We say the probability of more than one event at a time, and often we see this right here. We say the probability of A or B. Okay, so if the probability of A is just however many things are in A divided by the total number of space, if we were to consider, A or B, we'd say another set in here, A or B. What we could do is we say how many things are in A, how many things are in B total. We could just add those together and then divide by the total amount of outcomes that there are. Okay, so it's pretty simple to think about here. Let's go ahead and review with these pictures up here what we mean by A or B. When we say A or B, of course, like we just sketched over here on the right, we mean the number of things in A or the number of things in B. So if we wanted to find the probability of one or the other, what we could do is we could just simply count up how many outcomes are in each one. So for example, when you're looking at this picture here, we say we have 5 things in A, there are 4 things in B. So if I wanted the probability of, say, A only, it'd be 5 out of the total space. The probability of B only, it'd be 4 out of the total number of outcomes. But in this case, we say if I wanted A or B, we could just say it's the probability of A plus the probability of B. I mean, we could just simply add these things together and we would get 9 total outcomes out of the total space up in this image here. So when we talk about the probability of A or B, it's really kind of a simple formula. This is what we want to have in our back pockets. It's the probability of the first thing plus the probability of the second thing. So this formula right here, we actually use this whenever we find the probability of one event or another event. You could think of this word or in probability as really being replaced by a plus. And we'll find the probability of each event and just add those things together, okay? Now, the thing is, you'll notice the picture up here, A and B, they don't overlap at all. We would refer to these events as being mutually exclusive from one another. So when we talk about events being mutually exclusive, it means that they had no things in common to begin with. So we can get away with just saying, well, there are 5 here, there are 4 here. A or B would be the total of that. That's 9, okay? When we have 2 sets that do overlap, so this would be the non-mutually exclusive case that you see here in the middle. Non-mutually exclusive means that they have things in common, okay? It's not as easy as just counting things up. If I were to say probability of A or B, we could just say, couldn't we just find the probability of A and the probability of B and add those things together? And, we could talk about this. It would look like this. We'd say, well, how many things are in A, just by itself? We'd say, well, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 total things. Can't we just add that to how many things are in B right here? So add that up with these, 1, 2, 3, 4, 5, 6, 7, 8, and get 17 total. But when we say it's in A or B, what we're doing is we're considering how many total things are in their joint set here, together. And if we were to take the time to actually count all these up, we'd see we don't get 17. We get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 total. So how is it that we're ending up with 13 when really in the last one we were able to just add the number of things in each one up? The thing is, when you added up this original 9, what we had done was this. We had included these 4. It was these 5 out here plus the 4 in the middle. But when you added up this 8 right here, you say, well, there are 8 things in B. True, I mean, there are 4 things out here, but you counted the 4 in the middle again. So really what we've done is we've counted this middle section twice, okay? So this middle section, very quickly, I want to refer to this picture over here on the right. We refer to this middle section right here as the intersection of A and B. And when you think about the intersection of 2 things, where they run into each other, the thing is we refer to this as A and B at the same time. Something that is A and B, in A and in B, is in this middle portion right here. So here's the thing. I mean, if we were to say, again, probability of A or B in this middle case where 2 things overlap, can't we just add 9 plus 8? No, we can't. But if we were to get 17 here, that would be off. And we say, well, how much is it off by? Well, it's technically only 13 things. It was off by 4. So here's what our tactic is going to be, our method. When we have mutually exclusive things, okay, we can get away with just adding the stuff together. When they don't overlap, we can just add what's in one and the other and just add it up and divide by the total number of things. But when it's probability of A or B, and they do overlap, the thing is we'll still do this. We say we'll find the probability of A plus the probability of B. We'll replace the or with the plus. But what we have to do is we have to acknowledge that we counted these ones in the middle twice. So since we counted them twice, what we'll do is we'll take however many are in the intersection of A and B, the intersection, and we'll subtract it off once. So the formula for finding the probability of non-mutually exclusive events, non-mutually exclusive events, looks like this. We would just simply say it's the probability of one plus the probability of the other. So 9 plus 8, we could still totally do this, but we're going to take 4 off of that because we counted the 4 in the middle twice. And formally, we would define this as this, minus the probability of A and B at the same time. We refer to this as the intersection of the two sets. Okay. So when we find the probability of A or B, we'll just add the two together, but we'll subtract off anything that they have in common. And one thing I want to mention is this: what if they don't overlap? You know, that would be this first case up here. We'll use this formula. Could we still use the second formula? And actually you can, because there's still probability of the first thing, however many are in the first thing, plus the probability of however many in the second thing. But we say take off all the ones they have in common. Well, we say the ones they have in common up here, the intersection of the two, is empty. So you'd be subtracting 0 in the first place, and you'd still get what you need to get. So we're going to run through 3 examples of each, mutually exclusive things and non-mutually exclusive events, and take a look at both and how they use these formulas to get through them. So take a look at these ones on the left here. We say a card is randomly selected from a standard deck of 52 cards. We say, what's the probability that I get an ace or a face card? So we're going to start by writing the probability here. We say ace or face. If we wanted to do this, we could say, well, first of all, are these events mutually exclusive? That is, when I draw the picture and I say, well, here are all my aces, do aces overlap with faces? And an ace is not a face card. So what we could say is these two events are mutually exclusive. In other words, we have 4 aces. Total face cards, well, there are 3 face cards, a jack, queen, king in each suit, and there are 4 suits, so we have 12 total face cards here. Basically, we could say there are 16 total cards that we're considering here out of the total of 52. So to rewrite this using the formulas we see here, probability of ace or face, we'll use this first formula right here for mutually exclusive things. We'll rewrite this as the probability of ace plus the probability of face. And we could just add these up. We say, well, what's the probability I get an ace? Well, probability I get an ace is 4 out of 52. We say 4 out of 52. Plus now the probability I get a face, well, that's 12 out of 52. And you'll notice we have a common denominator here. So we get 16 out of 52. And, you know, honestly, we could, you know, get our calculator out here and get this. We say 16 divided by 52. But we'd have about a, you know, you can see here, we have about a 30.7% chance, or 0.307. So we say about, you know, 30.7-ish% chance. Okay, so when things are mutually exclusive, we'll just rewrite it as probability of the first thing plus probability of the second thing. So let's run with this next one here. We say one 6-sided die is rolled. What's the likelihood of rolling a multiple of 3 or 5? So we say probability multiple of 3 or 5. So we could rewrite this. Since I can't have a multiple of 3 on a die, the only 2 multiples of 3 are 3 and 6, and the only multiple of 5 is 5. They don't ever share a common multiple. We could say this is probability of multiple of 3 plus the probability of multiple of 5. And so we say, well, the multiples of 3, how many numbers are multiples of 3 on a die out of 6? We say 2 of them. 2 of them. I'm thinking 3 and I wrote a 3. Sorry. There are 2 numbers that are multiples of 3. And we say plus now how many are multiple of 5? Well, there's only one number that's a multiple of 5. That's our 5. So we could say, well, how many total is this? We say 3 out of 6. This is a half, or 50%. Okay. And then one more. We say, what if we roll a 6-sided die again? What's the likelihood of rolling a 2 or an odd number? So we say probability of 2 or odd. Okay. Since I can't roll a 2 and have it be odd at the same time, these are mutually exclusive events. So we could say, we'll just rewrite this as probability of 2 plus the probability of odd. And we'll find each individually. So what is the likelihood that I roll a 2? Well, there's only one 2 out of 6. Plus now, how many odd numbers are there? Well, there's 3 out of 6, so we get a total of 4 out of 6. or 2/3, or about a 66.6% chance. Okay, so this is for mutually exclusive events. We'll just rewrite it as the probability of the first thing plus probability of the second thing. It's pretty simple to do. So what if they are not mutually exclusive? Well, let's consider what we have here next. We say a card is randomly selected from a standard deck of 52 cards. What's the probability that it's a heart or a face card? So to write this first is what we need to do. We say probability that I get a heart or a face. Okay, so now we can get away with just saying this. Well, it'd be the probability of a heart plus the probability of a face card. I mean, that's the simplifying factor here. But notice this, there are face cards that are heart. There's the Jack of Hearts, there's the Queen of Hearts, and there's the King of Hearts. So we need to subtract off all of those, the probability of a heart and a face at the same time. So we're using this second formula right here where we have to take off the ones that we had counted twice. Okay, so we say how many hearts are there in a deck? We say, well, hearts, there are 13 hearts out of 52 total. Plus now how many face cards are there? Well, we say 12 face cards out of a total of 52. But see, recognize this, when we counted the hearts, we counted the Jack, the Queen, the King of Hearts. And when we counted the face cards, we also counted the Jack, the Queen, the King of Hearts. So now we get to subtract off all of those that were both a heart and a face card at the same time. And there are 3 cards that are hearts and face cards at the same time. So we get this, we get 13 plus 12 is 25. 25 minus 3 is 22 out of a 52 chance. And of course, we could get a decimal and a percentage for this, but I'm going to go ahead and move through these next 2 examples. We say, how about this? One 6-sided die is rolled. What's the likelihood or the probability of rolling a multiple of 3 or a multiple of 2? So we say probability of multiple of 3 or 2, and we'll consider these to be multiples, you know. So we say, okay, well, this would be probability of 3 plus the probability of 2. But since I can have something that is a multiple of 3 and 2 at the same time, that would be like the 6, we can say, well, we'll take off the probability of multiple of 3 and a 2 at the same time. So we say, all right, well, what's the probability I get a multiple of 3? Well, there's the 3 and the 6, so that's 2 out of 6 chance. We say, what's the probability I get a multiple of 2? Well, it's the 2, the 4, the 6, so that's a 3 out of 6 chance. Now we need to take off all numbers that are both a multiple of 3 and 2 at the same time, and that'd be a 6 on a die. So we'd say that's a 1 out of 6 chance. So we get this, we get 2 plus 3, which is 5, minus the one we counted twice, which is 4, so we get a 4 out of 6, or a 2/3 chance. Okay? And the last one here, it says a number cube is rolled. What's the probability of rolling a number less than 4 or an even number? Okay, so remember on a die, you know, we say a die looks like this. Suppose I could draw the picture 1, 2, 3, 4, 5, and 6. We say the probability of this, we get this, a number that's less than 4, whoops, or an even. So we'll start by writing the probability we want to find, and then we'll rewrite this using our formula that says, well, it's just the probability that something's less than 4 plus the probability that something's even. Okay, but we need to subtract off the probability of less than 4 and even. Sorry for squeezing that in there. So we say, all right, well, probability of numbers less than 4. Well, we have 3 numbers, 1, 2, and the 3 are less than 4, so we get this. We get a 3 out of 6 chance. Now, what's the probability it's even? So we say, well, that's my 2, my 4, and my 6, so that's a 3 out of 6. But we have to take off the probability that it's less than 4 and even at the same time. And of the numbers that were less than 4 and even at the same time, there was one that's also, or of the numbers that are less than 4, there's one also that is even at the same time, and that's our 2. So we say, well, minus the 1 over 6. We say 3 plus 3 is 6, minus the 1 we counted twice there, so we get a 5 out of 6 chance. So this is how you would use these formulas to find some compound probabilities.